All right, hi everybody. Welcome back to Tuesday, April 28th. I don't know where April went, but whatever, it's almost over, so that's cool. What we're doing today is we're looking to analyze graphs to determine how an engine works. So this is kind of maybe the day that we've been dreading about thermodynamics. It's kind of us looking at all those graphs again. So we did a good job with it by the end of the unit when we did it the first time, so hopefully this goes well. It's a tricky topic though. There's a lot going on, there's a lot to kind of remember, and if we just look at the graphs and try to memorize stuff, that's going to be a problem. But if we really think about what's happening and what these graphs mean, then we'll be in a really good position. So that's kind of what we're looking at today. Like, what do these graphs mean and how can we get information of them? And where does that information actually come from? Like, why is this equal to that? Why is this equal to whatever? So what we're doing today is a quick little introduction about engines, just making this relevant. Then we're going to do a review about these thermodynamic cycles. Then I have some practice questions for you and then a free response type question. And this is going to be for Tuesday and Wednesday. So not just all on Tuesday, spread it out however you like. Probably just watch the video today, this little lecture, and then on Wednesday, try out these practice questions. And that's what's going to be due. I'll have some multiple choice type practice questions and then a free response style practice question. So engines are something that we use every single day. We used to use them every day, like when you drive or if you mow the lawn or anything like that. Whenever you kind of use a car, you're using an engine. So the types of engines that we may see in our car are these internal combustion type engines. And I'll just kind of play a quick little snippet of this. I won't play the audio because it'll kind of blow us away. But we have these pistons and we have these cylinders. Some engines have these 6 cylinders. Some have the 8 cylinders. I don't really know much about cars. I know that when I was buying my car, they were like, do you want a 4-cylinder or a 6? And then I was like, I don't know what the difference is. And then my dad was like, don't get a 4, you won't be able to drive on the highway. And I was like, okay. But yeah, so they got some stuff going on here. This one, I liked it because it had a real engine. This one's kind of cool because it just kind of shows, hey, the fuel is going in and we have this compression, we have this squeezing it, and then we have the gas going out, this kind of ignited gas. And this is how we're able to get our engine rolling and going. Let me X out of those. And that type of engine is going to be a little bit different than the engine that we're studying, because what we saw there, that's not a closed system. In what we just saw there, the gas is ignited and then pushed out through the exhaust. So that's not a closed system. That's the system where the amount of moles of gas that we have are changing. So what we're going to look at is a closed system. So that's what we're going to consider the situation where the amount of gas in our system is constant, it's enclosed, we can compress it, we can heat it, but the moles of gas is always going to stay the same. We're not going to look at situations where the moles are changing. So there's a type of engine, they don't use it so much in cars anymore. Just because it costs a lot of money, apparently. I was looking up a few reasons, because it seems cool. It's a cool little engine. But yeah, apparently they use it in submarines. I don't know how that happens. I think maybe it's easier to keep it heated and cooled. I don't know. But so it's a Stirling engine, and this one's a closed system, where the amount of gas that we have is contained in there. And it follows the cycle below. Now we're kind of seeing like, oh yeah, these PV diagrams. I remember those. So we're looking at this. And what does this mean? How does this explain these processes that's happening in this engine? So we have this fire going, and then we see all these lines on this PV diagram. So what we want to be able to do by the end of this is explain those cycles and talk about what's happening and how is this graph, how does it relate to the cycles that are happening in, should I try to point that image or that image? I don't know where it is. All right, so what we're going to look at today is how to calculate the internal energy of an ideal gas, calculate the work done as a gas changes volume, relate work, heat, and internal energy, read temperature off a PV diagram, describe a process graphically and in words, and describe 4 types of thermodynamic processes. So it's a lot, but hopefully remember a good amount from when we did it before. So the very first thing that we're doing is we talked about how we're going to look at a closed system. So a system is a closed environment which heat transfer can take place. And a good example of this is kind of like this piston over here, this gas cylinder where we're saying, hey, the walls of the cylinder are closed, it's compressed by this piston, and we're not adding gas to it, we're not taking gas away from it. So kind of like in an older engine, like one of those Stirling engines, we have the gas, it kind of stays the same. So we may have talked about before when we dealt with energy, you may have defined the system. If you were in my class, you defined a system. Excuse me, sorry. And you said, this is what we care about. We want to look at the energy in that system. So in this case, it's the same idea. We're defining a system, and we're saying that if the system is closed, we aren't changing the amount of gas that we have in it. We're not doing anything to add more more gas. But if we think back to our previous physics learning, when we worked with conservation of energy before, what we did was we defined the system, and we said if anything outside the system acts on it, if we have this external force acting on our system, that process is called work. So really the same thing is what we're looking at here. We're defining a system of gas, and we're saying if something happens, if this thing forces the environment, or if the environment forces our system, we have work. And this whole idea of this thermodynamic cycles and processes is really just one big look at conservation of energy, us saying, hey, where's the energy going? What's happening here? How are we changing the energy of our system? Which is exactly what we did back when we studied conservation of energy before. So it's the same idea, but now we're dealing with it at a more microscopic scale, and things are harder to see. We can't see potential energy. It's harder to think about kinetic energy, but that's what we're looking at. So the first thing we have to define is we're looking at conservation of energy. So we really have to think about where's the energy coming from in this situation. When we're dealing with this gas in an enclosed space, what kind of energy do we have? And the energy that we're really looking at is internal energy, and our symbol for that is going to be U. So we're going to say the internal energy of a system is the total energy, or the total of all the different kinds of energy possessed by the particles that make it up. So it's the sum of the potential energy and the kinetic energy of the gas molecules. So yes, they're going to have some potential energy. We're mainly going to focus on the kinetic energy. Like we can lift up those particles, and we can, if we get into chemistry, we can break the bonds apart, and there's chemical energy stored in those bonds. But we're really going to be concerned with how much energy is related to the kinetic energy of these gases, i.e. like how fast are they moving and how much mass do they have, pretty much their kinetic energy. One thing that we can remember is the kinetic energy is directly related to the temperature of our gas. So that's going to show up a little bit later, but kind of keep that in mind, this idea that if we change the temperature, we change the kinetic energy, and therefore we're changing the internal energy of our system. So the only way to change our internal energy is by having this change in temperature. And what we're going to look at is how can we do that? How can we change the temperature or the internal energy of our system? So we really have two options to do this. There's two ways we can go about doing it, and both of them they correlate, or they make sense with what we talked about with our gas laws and what we've been talking about before. So one way that we can increase the internal energy of our system is we can do work on our gas. We can apply some sort of force on it to compress the space of our piston, to compress the space of the gas. So we can force it, we can do work on it. When we talked about work back with conservation of energy, we said that work, if we do work on our system, we add energy to our system. Like if I have this water bottle here, right now it has some potential energy, but whatever. If I force it over some displacement, I give it energy. Right now it has no energy. Now it has kinetic energy. I'm forcing it over a displacement. So the same idea here. We say, hey, we can compress this gas. We can do work on it. So we can force it over some displacement, compress that gas, and that increases the internal energy. Another option, what we talked about at the start of thermodynamics, was that we can heat things. We can undergo this process of heating, where we add this thermal energy. We have this exchange of thermal energy to our system. So maybe this thing is on like a little burner. It's at a higher temperature. That temperature wants to come to equilibrium. So temperature will flow from the warmer heating coil to the colder gas and increase the temperature of that gas that's contained in there. So if we're looking at how these two processes work, and I kind of added an ing, made those words a gerund, I think, if grammar is working for me. But so they're really processes, which is why I kind of added that ing. So we can increase the internal energy by working. So we force it down. And if we think about that, that's going to increase our collisions. That's going to make this we're going to have more bouncing. We're going to have this higher energetic gas because we have these particles that are colliding more now. They're interacting more now. They're able to collide off the walls, change their speed more. And yeah, they're bouncing around more. They have more space to bounce around, and that's going to increase the energy and by default increase the temperature because we have less space now. We've added energy to it. And then the other one is heating. We said that if we add heat to our system, that's going to increase the temperature, and these particles are going to be moving faster. They're going to be more energetic, there's going to be more collisions, so we're going to be able to increase the temperature if we add heat to our system. So we got those two ways, working and heating, these two processes. And we can do it the opposite way. If we wanted to decrease the internal energy of our system, we could have our gas do work on our environment. So we can have the gas within that piston push that piston up, and it'll be forcing the environment. If you think about putting like a little box on here, it would be lifting up that box. Just like it takes me energy to lift something, this gas is giving energy to that box. It's taking energy from itself and giving it to the box. And then another way is we could remove heat. Let's say we put something that is at a lower temperature around our container, our cylinder of gas. We know that temperature is going to flow from warmer to colder until we reach this thermal equilibrium. So the heat will flow out and we'll lose our internal energy because kinetic energy will be transferred from the gas to the environment being anything that's not a part of our system. And we have a law that dictates this idea. That's a lot of cool words and stuff, but if we want to put math to it, we have this law. We have this first law of thermodynamics. And this first law of thermodynamics tells us the change in internal energy of our system is equal to how much heat we put into our system and how much work we do on the system. So in any thermodynamic process, the change in internal energy, delta U, is equal to the net heat absorbed by the system plus the work done on the system. So we have a positive delta U, we have an increase in internal energy. So this is our first law of thermodynamics, and we can use that in our responses. If it says, hey, what's going on here? How can you, is there any physics law or any physics ideas that justify what you're seeing? This is one of these laws that we can reference. We can say, oh, well, we can increase internal energy by either heating or working based on our first law of thermodynamics. And so if we're looking at this case where we increase the delta U, let's say we did both of these. Let's say we both forced on the gas and we added heat to it. We would see, well, we added heat to it, so that Q term is going to be positive, and we did work on the gas. So that work term is going to be positive. So we'd have a positive Q term, a positive W term, which would give us a positive delta U, which would tell us the internal energy of our gas, it increased. We had a positive delta U, a positive change in internal energy. So then this kind of begs the question, how do we calculate Q and how do we calculate W? So Q is going to be hard to calculate. Q will mostly have to be given to us unless we can do one of those analyses with the heat flow rate, which it usually doesn't ask us to do. But work is something that we can calculate. So how do we determine how much work is done on our system? So this is kind of going to come down to an equation that tells us, well, we've talked about work before. We've talked about work when we've done energy before, and we said that work is really equal to our force times our displacement. So how much force is applied to the system, this external force acting on our system, over some sort of displacement. So we would calculate work before. We do work is equal to force times the displacement. And here what we can look at is, well, we're kind of considering pressure and we're considering volume. So let's move things around until we can get to those variables in our equations. We know that pressure is equal to force over area. So let's replace our term for force with pressure times area. So let's kind of rearrange that. Force is equal to pressure times area. So now if we plug that back in, we can say our work is equal to pressure times area times our displacement. And if we look here, if we kind of picture this as a kind of tilt it, get a little isometric view instead of a head-on view, we see, oh, well, the volume of our system, the volume of our gas decreased. We had the area of the piston, and we decreased it by the amount that we displaced that top piston, the thing that's holding it all in. So the volume that we changed it by was this area of our piston times this displacement d. So we can call this change in volume A times d, or just change in volume. So our work is then equal to P, the pressure, times the change in volume. And if we could just kind of think about that, if we have a greater displacement, we're going to have a greater change in volume. and we're going to have more work. If we have to squish it a lot more, we're doing more work on the system. So one thing with this, and pretty much with all of thermodynamics, the signs are super important. So the signs are really, really, really important. And there's ways that we can think about it, like just memorizing, oh, if it goes this way, it's a bad. If it goes this way, it's positive. This way is negative. But we want to think about intuitively what is actually happening and what do the signs mean and where do they come from. So kind of general, not even general rule of thumb, the way it goes is if the volume decreases, so the volume of our system decreases, we're saying that we have to have work done on our system to do this. We did this in our labs, we did this when we had these syringes, but if you picture yourself holding a syringe, the only way for the volume to decrease in that syringe is for something to do work on the system. You have to compress it. You have to apply some sort of force on the system over some sort of displacement. So if the volume of our system decreases, work is done on the system. The particles become more compressed, which means their energy is increased. You have to apply an external force on the piston in order to decrease the volume. You're doing work on it. And by doing that, it took energy for you to compress it. That energy is going into our system. So if our volume decreases, the work on the system is positive. The system has work done on it. It's gaining that energy, so it's positive. If the volume increases, then work is done by the system. Work is done by the system on the environment. So the particles become more spread out, which means their energy decreases. By forcing the environment, the system is doing work on the environment. Energy is taken away from the system and it's given to the environment. I gave you that example before. But if you think about a little block sitting on top of that piston, it takes energy. You would have to expand energy if you were going to lift up that block, some sort of displacement. It takes the same amount of energy for the system, this piston, to lift the block to that same height. It took energy to do that, and then energy is coming from the system. So if our volume increases, we're going to call that negative work on the system. Our system is going to lose energy, give it to the environment. And then if our volume doesn't change, then that means that there's no work done. The only way for us to have a work term is to have this change in volume. So kind of just a brief little summary of that. If our change in volume is negative, the work on the gas is positive. So if our volume decreases, work is positive. Work by the gas is negative. If our container expands, then we're saying, oh, the volume change is positive, work on the gas is negative, work by the gas is positive. And then we kind of have these fancy terms that we talked about in our gas laws lecture. This idea of isochoric or isovolumetric means we have no change in volume, so we can't have a work term. So we have this information, we're ready to start looking at graphs. But one thing that we have to define, one thing that we have to talk about is what a thermodynamic state is. So we have to define this term of thermodynamic state. So a state is really a combination of the four variables that are part of our gas law. So our gas law, PV equals nRT, includes the pressure, the temperature, the volume, and the amount of moles of our gas. So a state is just saying, what pressure are you at? What temperature are you at? What volume are you at? And how many moles do you have? So we have to have those four things make up a state. And a process, if we're going to define a thermodynamic process, it's really just changing our state. So how are we changing our state? How are we changing the pressure? If we change our pressure, that was a process. If we change our temperature, that was a process. If we change our volume, that was a process. If we change our number of moles, that's a process. If we change any of those, we could change all of them. We could change one of them. We could change two of them. We could change three of them. That's a process, causing some sort of state to change. So really quickly, let's give a first law a little try. Let's see how we can do with this. So let's say a gas absorbs 400 joules of heat while doing 120 joules of work on the environment. What is the change in internal energy for the gas? So give this a quick go, give it a quick thought, and then we'll pick it right back up in a second, but give it a quick thought. All right, so in this case, it looks like we're adding heat, so that's going to be a positive heat term, so positive 400 joules of heat is added to our system, and it looks like work is being done by the system on the environment. So we're losing, our system itself is losing 120 joules. So if we're using our first law, we have change in internal energy is equal to a positive 400 joules minus 120 joules, which gives us a total change in internal energy of our system of 280 joules. So we have this change in state, we have this process, and in doing this process, we have added 280 joules to our system. So then we talked about this pressure and volume and how we can get work from there. So what we can do to go a little bit further is if we have a pressure versus volume diagram, which is really going to be the main way that we look at our systems and the cycles and the changes of our states, if we have one of these processes, the area under the curve of a pressure versus volume diagram is going to equal the work. So the work under a pressure versus volume diagram is going to tell us the work. I think I said the work done. So the area under a pressure versus volume diagram is going to tell us the amount of work. And that kind of comes from, we'd have to do some integration, but it really falls out of this idea where work is P times V. If you want to find it for a more curved slope, then you would say, oh, well, we'd have to do some integration to find that area. But if we just look P times V, we'd have pressure on our y-axis, V on our horizontal axis, our x-axis, and the area bounded that would just be pressure times volume. So the area would be P times V, which would equal work. And again, finding the actual amount in most cases would require some integration, but we're not going to do that. It'll either give it to us or we'll have to just find it for a straight line. But so let's think about this before we dive in and kind of analyze a full cycle. So if we look at one change in state, one process, if we go from A to B, really quickly I want you to think, going from A to B, would that be positive work on the system or negative work on the system? So give this a quick thought, and then let's think about it. So if we go from A to B, we see, oh, my volume went up. The volume of this container of gas increased. So we know that if the volume goes up, that means that the system is doing work on the environment. It's pushing outwards on the environment. So we see going from A to B, we'll have an increase in volume, which means negative work on our system. So the volume increases, work on the system is negative. Our system gave energy to the environment. It pushed on the environment. It had this energy. It gave it to the environment. This one again. So then that was one process. That was going from one state to another, state A to B. What we can do is for a full cycle, we can say, let's change all of our states and then end up at our original state. So if we have this PV diagram, we can go through any amount of states. If we end up back at our original state, we have what we call a cycle. So we can go through a bunch of steps and then end back up at our original state, and that's a cycle. And really each little point on here represents a state. It represents a specified pressure, a specified volume, specified amount of moles, and then we could calculate the temperature using PV equals nRT. But so yeah, we can go through many different states, and then if we end up at our original state, that's a cycle. And then we can look at the area bounded, which we'll talk about in a second. But really one of the main ideas is that in a cycle, the change in internal energy is equal to 0. So this is a huge idea. In a complete cycle, the change in internal energy, this delta U, is equal to 0 joules. So if we start at the same state and we end at the same state, the change in internal energy from that same state to itself is 0 joules. So if it returns to its initial state, then it has the same internal energy as where we started. And if we think about where that comes from, it just comes from our gas law. This idea that PV equals nRT. So we said, okay, if we want to change the internal energy, we have to change the kinetic energy. And to change the kinetic energy, we have to change the temperature. So we're looking at PV equals nRT, where T is the temperature. And if we look at every state on here, well, if we start and end at the same location, that starting and ending point has the same pressure, it has the same volume, has the same amount of moles, which means if we use our gas law, PV equals nRT, it has to have the same temperature. So if we start and end at the same temperature, it has the same internal energy. So that's why throughout a complete cycle, at the starting point and the ending point, which is the same point, the same state, the internal energy is going to be the same, so our change is 0. So what we can look at really quickly is kind of the direction of this flow, the direction of these processes. So here we're going, that is clockwise, and that's going to be a heat engine. So what we can look at here is kind of looking at each cycle. So if we go from down at this state to this state, so each process, not each cycle. If we go from this state to this state, we can see, well, we have this volume decrease, so we have positive work done on our system. If we go from here to here, well, let's just say that it's kind of straight up. We don't have any change in volume. If we go from here to here, this state to this state, we have an increase in volume. So we're saying, oh, well, that increase in volume means negative work is done on our system. Energy is applied to the environment, or added to the environment. So then we can also say, well, this area that we had that was positive work is canceled out by this area of negative work, and we're really just left with what's bounded. So if we look at this cycle that's going clockwise, we can say overall, the net energy is given to the environment. So we can say overall work is done on the environment as a whole. So this work on the system, the system is doing work on the environment as a whole. And let me skip ahead really quick. So if we look at that, we can use our internal energy, our first law of thermodynamics, and think about what's going on there. We said in the system where we have this heat engine, this system that's going clockwise, we have negative work done on our system. And if we look at this, we said, well, for a full cycle, the change in internal energy has to be 0. So W plus Q has to be equal 0. So in that full cycle, if we have a negative work, we have to have a positive heat added to our system for us to have a change in internal energy of 0. We're looking at that delta U equals W plus Q. We said for this case, we have a net negative work done on our system because work is done on the environment. So it's lost from our system to the environment. In order to make that change in internal energy equal to 0, we have to add heat to our environment, or to our system. So we have this heat engine that has heat added to our system. If we look at the opposite, if we're going counterclockwise this time, we can look at the same idea, except for this time, the total work done on the system is positive. So overall, we have this positive work done on our system. And look at here, again, if we're using this first law of thermodynamics, we have a positive work. Then in order to get this total change in internal energy throughout this cycle equal to 0, we have to have negative Q. So heat is taken from our system, and that's a refrigerator. So it's kind of cool how we can think about the direction of this and think about how this relates to our first law of thermodynamics. And keeping in mind that the change in internal energy for a full cycle has to equal 0. So that's a lot, but yeah. So yeah, now we're just gonna try out a few things. So here we have this cycle, and what I want you to do is think about what is the work done along each leg of the cycle, and then what's the total work done by the gas. So done by the gas on the system. So think about that really quickly. Take a second, and then we'll go over it. All right, cool. So let's just start at this state over here. Let's start at this state and say, okay, when we're going from a volume of 1 to a volume of 1, that doesn't have a change in, or that doesn't have a work done on it, right? Because we're not changing the volume. We said in order to have a work done on our system, we have to have this change in volume. So here we have 0 joules of work. So that's something. And then the next one, if we look at it, well, we said that the work is just going to be the area underneath. So let's take this and say, well, this has an area of 1, 2, 3 atmospheres times 1, 2 liters. So we have 3 times 2. So this has an area of 6. And there's units, but whatever. So that has an area of 6. And that looks like work is being done on the environment by the gas because we have this increase in volumes. The volume's going up, so we have this positive work done by the gas. Usually we look at it as a focus of what's happening to the gas, But here it's asking us for the total work done by the gas. So that's going to be positive. Positive 6 done by the gas because it's increasing its volume. So work is done by the gas on the environment. So we got 6 there. Here we have no change in volume. And here we have a negative. So that's going to be 1, 2 times 1, 2. So that's going to be 4. And again, we're going to call that negative because we're looking at work done by the gas. So we have 6 and 4. And then we have to take into account the units, which I didn't do. So we have 600, 400, and that gives us 200 done by the gas. If it had asked for the work done on the gas, we'd say, oh, well, it's going to be the same everything, same calculations, but the sign is going to be different. So that's going to be a negative 200 of work done on the gas. But this was asking for the work done by the gas. So it's going to be positive 200 joules. All right, then our favorite part, the 4 processes that we're going to look at. So we have 4 things to look at, 4 cycles, 4 processes. We have isochoric, where we have no change in volume, isobaric, where we have no change in pressure, isothermal, where we have no change in temperature, and adiabatic, where we have no heat added. So the first one we're going to look at is isochoric. In an isochoric process, we're going to say we have no change in volume. Our volume is going to stay constant. And because our volume is not changing, we're going to say that the work remains the same. So the system, the container, it's not expanding, it's not being pushed down, it's not pushing on the environment. So the work is going to equal 0. There's no change in volume, so that work term has to be 0. Then if we look at our first law of thermodynamics, we can say, oh, well, our change in internal energy during this process has to come from heating. If we change the internal energy, it's only going to come from heating. So either heat leaving or heat entering our system. But that's going to be the only way to change our internal energy through an isochoric process, because we can't change our internal energy by working, by this compression or this extension. So if we wanted to do this in a lab setting, we'd say, okay, well, we have to make this container rigid, ensure that the volume's not changing, and then add some sort of heating element if we were going to change the internal energy. So either put it on like a hot plate or put it in ice in order to change the internal energy through heating. And if we were going to graph an isochoric process, we'd say, well, the volume's not changing, so that's just going to be a straight line. So it's going from a change in pressure, but the volume is constant throughout. Again, with this, kind of relating it back, we see there's no area under that, it's just a line, so there can't be any work associated with it. All right, if we look at an isobaric process, or isobaric, we have no change in pressure. We have the same pressure throughout. So with this one, there's no really special way to do anything. There's no like special like, oh, there's no Q or there's no W. We could have heat, we could have work. The benefit of this is that work is very easy to find. If we are given one of those P versus V graphs, the work is incredibly easy for us to find because it's just going to be a straight line. So for like this case, we can have this constant pressure term. We can add heat, we can take away heat, we can change the volume, and we can change the volume, whatever, accordingly. So to do this, it's kind of, we're going to have to do this tricky balancing act. If we wanted to change the, which one would that be? If we wanted to increase the volume, but keep the pressure the same, we'd have to increase the volume. So work would have to be done on the environment by the system, but we'd have to add heat to make sure that when these particles lose energy from this decompression, from this expansion, we're replacing the energy that we lost from the heating term. So we kind of have to keep those two balanced with each other. And then I'll keep the pressure constant. And then kind of the opposite, if we were compressing the piston, this would increase the pressure traditionally if we did nothing else. So we'd have to take away some of that energy via heat by cooling it so that we don't increase the pressure, and that'll keep not the volume constant, but the pressure constant. All right, and then like I said earlier, this one, it's really nice to find the amount of work done because this line is just a straight line. This will give us a constant pressure. Everywhere we look at this, it has 3 atmospheres of pressure. So we have no change in pressure. So the volume and pressure, the area bounded by that is just gonna be a square, which is super nice. We love the area of a square or a rectangle, whatever. And then isothermal is gonna be the same temperature. we said before that if we wanted to change the internal energy of our system, we have to change the temperature. We're changing the internal energy by changing the kinetic energy, which is related to the temperature. So if we have no change in temperature, then we have no change in internal energy. If we look at that first law of thermodynamics, if we have delta U equals 0 and delta U equals Q plus W, then we'd say the heat is equal to negative work. So, or work is equal to negative heat. So we have no change in internal energy. So to do that, that's kind of a tricky balancing act. It's a situation where we have to try to figure out, okay, if we want no change in internal energy, if our work is done by the gas on the environment, so if we have this negative work being done on the gas, then we have to add heat to compensate for that loss of energy via work. Or if we do work on our system, we have to take away heat to compensate for that gain. So if we look at this isothermal process, we say this W has to equal to Q, and then we have this nice kind of like inverse graph for our line for this process. But how do we know that it's an inverse graph? This relates directly from the gas law, this idea that PV is equal to nRT. If we have an isothermal process, then T is going to be constant. So we're really saying, well, how does pressure change with volume at this space where T is constant? If T is constant, we see, well, pressure is just going to change with the inverse of volume. So that's just going to look like an inverse graph. Isothermal is also a little bit tricky because we have to check. We have to check usually to see if it is isothermal. So we have to see, does PV over here equal PV over here? And if PV equals PV, PV is always going to equal the same nRT because that T is constant. So we have to check, does PV at one location or at one state equal PV at another state? If it does, we have this isothermal process. Then the final process is adiabatic, this process where the heating term is 0. So with this one, if we change the internal energy of our system, really the only way that we're changing it is through work. So either compressing it or expanding it. So no heat is added or subtracted. Any work done comes from the expense of internal energy. Changes in U make the piston rise or fall. And the way to do that is just either expand or compress your piston or your container without heating it. So without any heating elements added, no ice, no heat, no burners, nothing. And with adiabatic, it's kind of the hardest one to identify. It looks kind of like isothermal, except for PV does not equal PV. Yeah, and we can find the change in internal energy from directly finding the area underneath our graph. The area is going to be a little bit harder to find because it's curved, but usually it'll give it to you. It'll say something like, oh, the area under here is this many joules. And then the final little bit. So if we want to change the internal energy, we can change the internal energy by changing, and this is what I said earlier, but I just want to kind of restate it and give you an equation for it. We can change the internal energy by changing the kinetic energy of our particles, because changing the kinetic energy is directly related to changing the temperature, and a change in temperature results in a change in internal energy. So to change the internal energy, we have to change the kinetic energy. To change the kinetic energy, we are changing the temperature, pretty much, of our gas. So if we wanted to get an equation for this, this equation is not on the AP equation sheet, but you can derive it from what's on there. I don't know if we need it or not. I'm still confused about it. It's not in anything that says, hey, teach this, but sometimes it shows up in problems, and they did talk about it in like the AP review. So I just want to talk about it really briefly. So if we're looking at this, we have this equation for one particle. For the kinetic energy of one of these particles, we can say K, kinetic energy, is equal to 3/2 times KB, the Boltzmann constant, times the temperature. For n number of particles, where n is just an amount of particles, we can say the kinetic energy of those n particles is equal to 3/2 times the amount of particles we have, times the Boltzmann constant, times temperature. If we change our kinetic energy, we're saying that results directly in a change in internal energy. And the way to do that is to change our temperature. So I just kind of added a delta in there. So then what we can say is, well, based on our ideal gas law equation, we had one equation that said PV equals little n RT, and we had this one equation that said PV equals big N KB times T. So we can replace NKB with NR, So we can say change in internal energy is equal to 3/2 times N times R times delta T. Or we can say nRT, that's just our ideal gas law, what's equal to PV. So we can say, or we can just write it as nRT is nR times change in T is the change in pressure and the change in volume multiplied together. So these are two equations where we can find the change in internal energy. Again, I'm still not sure if we need to do that or not, but we'll roll with it. All right, so if we're looking back at this engine, kind of the last little bit, well, if we look at this process down here that's given for what's going on up here, we can say, well, from step 1 to 2 for this process, we can say, well, the heating increases the volume and it expands. We see that it has this change in volume where we have this expansion and the volume is going up, so work is done on the environment in this step. So that's kind of like, hey, it's pushing on the environment. From 2 to 3, we have this decrease in pressure at a constant volume, so we have no work done. 3 to 4, we have work is done on the system, and the volume of our gas is decreasing, so that's kind of this recompression. And then 4 by 1, we heat the gas in here, and that pressure increases so that it can then go and push. But that's happening at a constant volume. So kind of an explanation from where this GIF came from for what's happening. It says air in the engine is cyclically heated by an alcohol burner and expands to push the power piston, shown in blue, to the right. As the power piston moves to the right, the yellow linkage forces the loose-fitting red piston on the left half of the machine to displace air to the cooler side of the engine. The air on the cool side loses heat to the outside world and contracts, pulling the blue piston to the left. The air is again displaced, sending it back to the hotter region of the engine, and the cycle repeats. Whew. All right, so that's what I have for this little lecture. The rest is going to be practice.